Hi, my name is Krisha Basar, and I will be talking about my project, which is about using genetic algorithms to make AI race cars. So how can neuroevolution of augmenting topologies, which is just a type of genetic algorithm, be used to train cars to race? So this is just a brief table of contents of what I will be going through throughout this video. So I'll start off with an overview of neural networks. I'll explain what neural networks are and how they work. Then I'll move on to genetic algorithms and NEAT. I'll explain what those are. And then I'll be going on into how I implemented my AI and the data and results I got from the AI. All right, so let's start with an overview of neural networks, and I'll explain what they are. So it is now more clear than ever that artificial intelligence is the future, right? It's everywhere around us. So just one example of artificial intelligence is neural evolution. And so what neural evolution is that it relies on two major things: neural networks, which I'll talk about, and genetic algorithms, which is also something I'll be explaining in this video. And right here, I have a picture of a neural network. Now, many people think like artificial intelligence is going to take over the world and this and that, but what it really comes down to is just math and a few lines of code. So, all right, so let's get into the structure of neural networks. So neural networks are nothing but a collection of neurons or nodes, and they're interconnected in several connections and are organized in layers. So if you look on the picture on the right, you can see the dots are neurons, and the lines are a connection in between the neurons. And the purpose of neural networks is to take in data, perform a series of calculations, and recognize a relationship. So if I were to give it pictures of a clothing, for example, it should be able to output, oh, this picture is a t-shirt, or this picture is a picture of a sock. And that's just one application of a neural network. There's many different applications. So the leftmost layer is the input layer, which is a series of nodes that take in data that is given to them. So in the example of pictures of clothing, it would take in images of or pixels that represent images of clothing. And the rightmost layer is an output layer, which takes the data from the previous layer. So there's different layers. It takes in the data from the previous layer and it determines the final result. Now, the layers in between, the left and the right, everything in between is called a hidden layer. And these layers are where most of the computation is done. So it's where most of the math happens. It's where all the calculations happen to find out whether this image of a shirt is actually a shirt, or is it a sweater, or is it a sock, and so on and so forth. So I'm going to be just sticking with this example of a clothing or pictures of clothing just to help explain what neural networks are. So for now, I want you to think about a node as a place that holds a number. And so each connection in the neural network also contains a number called the weight. So each connection has a weight. And so the information processing mechanism, so the neural network, can be thought of as a system in which activations from one layer bring about activations in the next layer. So let's say several nodes are activated in the input layer, that's going to bring about the activations of several nodes in the next layer, and so on and so forth, until it activates a node in the output layer. And that's going to determine our output of the neural network. So how exactly does the neural network know which neurons to fire? So how does it know which ones to activate, which ones to not activate? So let's get into that. So in order to calculate nodes, a neural network takes the value of each previous node that connects to the node is attempting to calculate and multiplies that number by the weight of the associated connection. So what all that means is, let's say you have a node, right? A node in your input layer and a node in your second layer, which is also a hidden layer. And let's say that node from the input layer has a connection to a node in the second layer. So what's going to happen is that in order to calculate that node in the second layer, it's going to multiply the number that's inside the node by the weight of the connection that connects both of the nodes together. And now it's going to repeat that sequence until it has calculated all the nodes, and then it's going to all the nodes that connect to that specific node in the second layer, and then it's going to add all those numbers up in order to find the a sum, right? And that sum is going to be put into an activation function, and the output of that activation function is going to be the number that's stored inside the new node. And so all those words can just be squished into this equation, mathematical equation that's shown in the picture on the right. So you can see for each node that connects to the second, that has a connection to the node in the next layer, we're going to take the number inside those nodes, we're going to multiply it by the weights of their connections, and then we're going to add all of them up. Now, I mentioned activation function earlier. So what are they? So activation functions, basically you put in a number, which is in this case is going to be a sum, and it's going to basically squish that number between a range. So there's many different activation functions. So there's sigmoid, for example, there's rectified linear unit, while many people refer to them as ReLU, and tan H. And basically, for example, some activation function will squish the number between -1 and 1. Some will squish it between numbers very small, and then or it'll make the number very large. And so they're basically just functions that squish the number between a certain range. And after that activation function, it's going to have some type of output. So if it's going to be an output, like if you're using a function that squishes it between -1 and 1, it's going to have an output that's maybe very close to -1, or it's going to have an output maybe that's very close to 1. So now that we know how nodes are calculated and how the basic format of a neural network is, again, this can get very complicated. I haven't even talked about biases, but I'm going to keep it simple for this video. So I'm going to get into how the neural networks are trained, which is like the AI sort of part of it. So plain neural networks learn through a process called backpropagation and gradient descent, which for my project, which I'm using NEAT, is not going to be what's happening. It is sort of it to an extent, but not so much. But these are just in general for neural networks. So in backpropagation and gradient descent, what happens is that it basically, in a sense, tweaks the weights and biases of the neural network in order to reduce the value given by a loss function. And what's a loss function? So a loss function is basically a function you put in your numbers and it spits out a number or a graph of numbers that will determine how bad your AI is. So let's look at the graph on the right here. This looks like a really fancy, cool graph. This could be a graph given by a loss function. And if you notice, it has certain peaks and has certain dips in the graph. And what we want to do is we want to reduce the number given by the loss function. So we want to go down those hills. And what gradient descent is, it's basically an algorithm that will try to reduce the number given by a loss function by the fastest amount. So think of yourself on top of a mountain and you want to get down into the dip as fast as possible. Well, you're not going to go spin around the mountain. You want to go all the way straight down. So what gradient descent is, it will find the fastest way to go down, and it will just keep going down until it reaches a dip in your in the loss function graph. Well, it gets a little more complicated because you could be stuck at something called as a local minima or global minima. Well, what happens is you want to reach a global minima, which is basically the largest dip in your entire graph. So in this case here, it's going to be the rightmost dip, but you could get stuck on a dip on the left. And so there's several algorithms to fix that. That's just some issues that happen with gradient descent and backpropagation. But I won't be getting into the complex stuff with that because it's not really what I'm going to be using for my project. Anyways, a neural network is given labeled data. So this is the training part of it. So let's say I want to train the neural network, right? So what I'll do is that I'll give it labeled data, which is sort of like giving a student a practice worksheet with answers on the back. And what happens is the neural network takes its guess on the first question because it has no idea what it's doing in the first time. And it's going to look at the answer key to see how off it was from the correct value. So if you're giving a student an answer key, a worksheet with an answer key on the back, the student is going to answer those questions and look on the answer key and then see how off they were or how many questions they got wrong. It's going to notice, oh, I'm pretty bad, right? This is our first time. So what it's going to do is it's going to keep practicing and practicing. It's going to tweak its weights and biases accordingly until it reaches a certain accuracy. And once this neural network is trained, or once this neural network has reached a certain accuracy, we call it trained neural network. And this basically has a certain accuracy, and it could perform the task pretty well, right? So if you give a student lots of practice worksheets to keep checking their answers on the back, they were like, okay, I've made a mistake here, and let me fix it. It's going to keep doing that until it gets better and better, until the student has reached a certain accuracy. So on the test, they get 100, hopefully, right? So that's basically how neural networks train. And this is a really, really oversimplified way of saying it. Again, it gets really complicated. I don't want to get into the details for this video. So I hope you understand that part. All right, so now let's get into section 2 of the video, which is genetic algorithms and NEAT. Alright, so genetic algorithms are algorithms that take advantage of the process of evolution, and they try their best to mimic natural selection. So neural evolution of augmented topologies, which is just a long form of saying NEAT, is just one of many genetic algorithms that exist. And what NEAT does is that it changes the weighting parameters and the structures of networks, while also attempting to find a balance between the fitness of evolved solutions and their diversity. So what does that mean? So in other words, what NEAT does is that each genome, so each individual in a population will have its own neural network. And what's going to happen is that it's going to try to tweak the values or tweak the connections and the nodes in each of those individuals' neural network until it finds a pretty good species of individuals that have a high fitness value. Fitness just represents how well they did in their environment. And it's going to try to diversify the population. So it's going to try to find an alpha species, a species that does very well, or a species that does not actually do very well. And so it's going to try to be diverse in order to find a very well performing species. And the picture on the right is actually a neural network. I know it does not look like one based off what you saw in the previous section. Well, the neural networks in NEAT are very different, sort of. What happens is that they do not really have layers. The nodes sort of form on the connections of other, the nodes sort of form on the connections between other nodes. And I will talk about that more on the next slide. So let's talk about the evolution process now. So each member of the population, again, NEAT generates several individuals, which represent, they're all each part of a population. So each member of the population starts with the simplest form of a neural network, which is something I explained previously. NEAT changes the topology of the neural networks based on the performance of the population. Topology basically means the structure of the neural network. So it will basically change the connections, the nodes, and tweak this and that of each neural network based on the performance or how it performed in the environment. So neural networks used in NEAT do not have layers, which is also something I explained before. The nodes are added to various locations on the connections of each node. So each genome individual has two sets of genes. So they have node genes and they have connection genes. And these connection genes also have an innovation number. So I'll talk about that more right now. So as you can see on the right here, you can see a picture of a genome. And what this is going to have, it's going to have two different sets. It's going to have a node genes, it's going to have node genes, and it's going to have connection genes. And node genes are displayed on the top, the connection genes are displayed on the bottom. And each of these is very important into creating what a neural network looks like for NEAT. As you can see, there's a diagram. This is just a table format, and then there's a diagram of what this table would look like in the structure of a neural network. So let's get into connection genes. So connection genes actually have something called as an innovation number. And what this innovation number is it's basically represents when that connection was created, and these are unique to that connection. So if you notice, let's say the first connection has an innovation number of 1, which you can see on the bottom, which is the bottommost item in the box on connection genes. And so it's going to have an innovation number of 1. So its in is 1, which is the node number 1, and its out is 4, which is node number 4. So that connection there has an innovation number of 1. Now, if you notice, not all of them have different innovation numbers. And so you can see that, each of the connections have different innovation numbers. But I will get into when certain connections do not have different innovation numbers. And that is when the connection is connecting to the same 2 nodes in a different neural network. So what I mean by that is, like, you know how there's several different neural networks in each population. For each individual, there's different neural networks. So sometimes in one neural network, you'll have a node connecting from 1 to 4 in one individual, but in another individual, you may also have a connection between 1 and 4. So that will have the same innovation number. And the cool thing is that innovation numbers are shared throughout the entire simulation. So the one individual with the connection of 1 to 4 will also have the same innovation number as another individual with the connection of 1 to 4, and they will know that they have the same innovation number. And so a new connection gives it a new innovation number. So a new connection that is not previously present, that hasn't occurred anywhere else in the entire simulation, it's going to have a new innovation number. All right, so let's get into crossovers, which is one of the 3 stages of NEAT. So the 3 stages of NEAT are crossovers, selection, and mutation. So crossovers are done with just connection genes, because if you know the format of the connection genes, you also know the format of the node genes. So let's look at, this is just to clarify innovation numbers. Let's look at connection 2 to 5, which is the first row of boxes. And you can see that has an innovation number of 4, which is number on top of the 2, and then the arrow, and then 5. So that's innovation number of 4. And it's also going to have the same innovation number as the same connection on the right side. So on parent 2, you can see there's a connection gene with 2 and 5, and that's going to have the same innovation number, which is 4. So those two are basically the same connections. So the first step in crossovers is to pair the connection gene sets by the innovation number. So if you look at the rows of connection genes or the gene sets underneath the arrow, you can see that they're lined up by innovation number. And disable, just the DISAB basically means that the connection is disabled. The second step is to find the connection gene set of the offspring. So we want to find out what the offspring between these 2 parents are. So what we're going to do is that, let's say both the parents have the same gene. So if you look at connection genes 1 through 5, they both have both parents have those connections. They both have those connections with the innovation number. So what it's going to do is going to randomly choose between those genes. So offspring 1 is going to randomly have, the offspring is going to randomly have a gene from either parent 1 or parent 2 for genes 1 through 5. For 6 to 10, however, they do not have a matching pair. So those are known as disjoint genes. And so those do not have a pair. And so what's going to happen is that, let's say parent 2 is the only one that has connection gene 6, then it's going to inherit that specific gene. Now, excess genes are just disjoint genes at the end of the gene set. And why this is important is that if parent 1 was to be fitter, so fitness is how well the individual has performed. So if parent 1 was fitter, then the excess genes of parent 2 would be ignored, and the offspring will not inherit them. So hopefully that makes sense. And that's crossovers, the first stage of NEAT. So now let's get into mutations, which is the second stage of NEAT. So I explained before there are 3 stages, so this just happens to be the second one. And crossovers, what they do is they progress the species as a whole. They find offsprings between 2 parents, and it's basically how evolution happens, right? We come down to our parents, we get certain genes, and those genes are supposed to help us survive in the environment. And mutations apply an operation to an individual to introduce noise in the way that neural networks are structured. So what that means is that in order to diversify the population, there's going to be some mutation. So uh, sometimes just some examples of mutations are adding a connection at a node at a random spot, or you can add random nodes at random spots. So if you look on a picture on the right, there's a mutated connection. You can see it just randomly added a mutation or a connection gene. So what this is, the purpose of this is so that once the population is diversified, the algorithm can determine that, okay, it can see if this mutation performed well or not, and if it performed well, then that's great. Then most likely the offspring of this neural network is going to also have this mutated gene, and that's going to create a separate species, and that species is going to be perform much better than any other species that does not have this mutation. But on the other hand, if it does not perform nicely or does not do well in the environment, it's just going to ignore the mutation in several generations down if it does really poorly. And so NEAT can test out completely different variations of neural networks to see whether or not the individual performs well, which is something I just explained right now. All right, so now let's get into the third stage of NEAT, which is selection. So selection is a stage of NEAT in which genomes are chosen for later breeding. So NEAT compares each genome's neural network structure and speciates them into separate groups. And then it rearranges the genomes in each species by their score. So after it's formatted this, it knows how each species has performed. It's formatted it compared to other species. And score is basically how well the neural network performed. The next step in mutation is to kill off a certain percentage of genomes in each species. So the programmer will code in their config value, config sheet basically, which is the configuration sheet of NEAT, and they're going to code in some type of value. Like if, for example, if 50% is the cutoff, the lower performing half of the genomes will be killed off. All right, guys, so we have finally reached the third section of our video, which is implementing the AI. So this is how I wrote my own AI, what I did, and specific to this project. All right, so the first thing I did was that I created the game. And the first thing I did was I coded this game, which is basically a car moving around a track. And what the track does, it has no sensors, basically. It's just a bunch of black pixels laid out in the road format. The green is the grass. The car is not supposed to go on top of the grass. And I just coded basically a simple version where I can just control how the car moves left and right. And later I'll be implementing the AI. Right now I'm changing the speed and the steering, so I can increase the speed too, and it goes around much faster. And so when I implement the AI, I will not be using my keyboard controls, which is what I'm using right now, but the AI will be controlling it later on. The next thing I did was implement collision sensors or collision points, so which are the green points on the corners of the car. Whenever I go off the road, they turn red, and whenever I am on the road, they turn green. And so this is basically for the AI to know exactly when the car is off the road so that I can kill off the car and it will not survive that round. So right now I'm just driving the car over the green and over the black, and you can see how it's changing colors when I'm off the road and on the road. All right, so the next thing I did was add LiDAR rays to the car. So as you can see, they're basically just lines and dots extending out from the center of the car. And this will tell the car or the AI how far the edge of the road is from the center of the car. So depending on the length of these rays, it knows when to turn. So let's say in this case, while I'm driving here, the ones on the side are much shorter than the ones going forward. So you know that there's more space in front of you than there is on the side. So then it knows not to turn. And this is just me driving the car yet. I haven't implemented the AI, but that is the next step to do. All right, so now that I've started, I have implemented the AI, I'm just going to start up my program here so that you can see. And what's going to happen is that I'm going to have a bunch of cars that are going to be going around the track. So once I start this program, you can see that there are a bunch of cars that start off around the track. And what happens is that each of these cars is an individual in the population, and these cars are going to try to get better and better at racing each other. So that was the end of the first generation, which I have set it to be around 15 seconds, give or take. So the first generation lasted 13 seconds. And on the side, on the left side here, you can see my terminal returning all the statistics on each individual in the population. So you can see their fitness, you could see that generation's average adjusted fitness, you could see the best fitness, you could also see the standard deviation of each individual, and you can also see the generation time and how many species went extinct. So for now, there's only one species, but you can see that some cars are doing better than others because their neural network is more optimized for this track. So you can now see that there's a green car that's being left behind versus the cars in the front. So in this case, it looks like there's only one green car that's left behind in that generation. So that was probably a mutation that did poorly. But you can see now they're going to start to speed up a bit, and they're getting better and better at racing each other. So this is just the first map, and I have two other maps to show you. All right, so now I'm on my second map, and I just start my program here. And now you can see that this is a different map. So it's a little bit more curvy. It's going around the sharp turns, and already off the bat, you can see that there's already some neural networks that are pretty good at driving around these curves. So there's more and more surviving the first run, and now it's going on to generation one, and you can see that there's already a purple car that's much better than the others. The generation ended, and it's starting a new one. So between each generation, it's doing crossovers, it's adding mutations to calculate the next offspring, and it's also selecting which offsprings are going to survive the next generation and which are not. And you can already see that the average fitness is increasing. It went from 2,000 to 4,000 to 6,000. So it's increasing the average population's the population's average fitness, which is how well the population is doing overall. All right, so now I'm starting up my third map, which is a slightly more complex map. As you can see, very few of them are surviving the first right turn. And also we have a red car that made the turn. So there are two right turns over in this, and there is also a narrow section on the right side you can see. And I'm hoping to see the cars regroup in that section, come together, and then prepare for a right turn. And this is a very sharp right turn. Another thing interesting about this map that I wanted to try was that you can see they have a choice of either going on the bottom road or the top road, which there is one flaw of this map though. I feel like it is much easier for the cars to just continue going forward, so they mostly go on the top one. I rarely see them going on the bottom one. Something interesting I noticed though was that when I did go on the bottom one, they tried to gain as much fitness as they could by going in loops from the bottom track to the top track and then spinning around in circles, just so that they can gain as much fitness as they could before the generation ended. And you can see now that there are more and more surviving, and they're more and more making loops around the track. And the green one just tried to go at the bottom one, but it died off. So it's not exactly good. It will probably try again in the next generation. Okay, so it didn't, but that's fine. You can see how the cars are still getting better at going around the map. It went from 2,000 to 5,000 to 6,000, and that's the average fitness. Oh, so we have a purple one that went underneath, but it still died off, but it got farther than the other green one that tried going down. So that's map 3. So now let's get into section 4 of the video, which is the data and results. So as you can see on this slide, this is track 1's data. You can see I did 3 simulations of each map just to get some consistency going. And I took a trend line, which is basically average of each of the values of each generation. And on the left side over here, on the y-axis is the average fitness that's graphed, so how well they did. And you can see that they slowly increase over time and they sort of plateau at one point, and that's because the generation time, or how long the generation is, it's sort of a cap on how much distance they can gain, in that within that generation time. And in the beginning, they improved drastically. Again, this is track 1, so it's super easy for them to go around the track, and they sort of increase in fitness. You can see in simulation 2, however, there was several higher peaks. That's probably because they learned how to drive or increase their speed and still survive the map. And so that's track 1. Next track, which is track 2, you can see this is sort of a gradual increase, and you can actually see how they learned much better in track 2, since it was a little bit harder. They were failing in the beginning. They were getting between 5,000 and 15,000 as average fitnesses until they plateaued at around 17,000 average fitness. But you can see there were some dips. If you look in simulation 1, there's a huge dip. There's a huge dip by generation 15, which is the x-axis. You can see that generation 15, there was a huge dip. It did not perform well, maybe because that was a bad mutation that got carried on, or something just happened between generations there. So this is track 3, which is extremely hard, and you can see the difference between the other graphs, that the average fitness values are considerably lower. So you can see that they sort of very slowly start to learn how to drive. They're still increasing. So if I did test this out for more than 25 generations, maybe 100 or 200 generations, or maybe even 500 generations, they would have reached the fitness value to for the other roads. But I did not test it for that long for time reasons, because it would take a toll on my computer, and its computational power is a lot. So that's the data for track 3. So now we have finally reached the end of this video. So given that giving relevant data, I concluded was crucial to the neural networks, so that they can formulate an output in the responses situation that it's in. So in this case, I use LiDAR arrays as the input, and this was extremely important because when they're short, the neural network should recognize that, oh, it's close to the wall, and that it should try to turn in the direction where the LiDAR arrays are longest, which means that it has the most space. Now, creating multiple maps of various difficulties gave me insight on how neural networks behave and how efficient the evolutionary processes behind me is. So basically, I learned that by giving different maps, I see that they learn quicker on some maps. Some maps are sort of harder for them. You can see that through the data. And through analysis of the data, it's clear that on easier tracks, the AI learns to maneuver the cars with more accuracy and speed. So on the first map, they were much faster than, let's say, the third map at learning, and they were more accurate, so less of them died. And as the generations pass, the AI not only aims to increase the genome's fitness, but also an entire phenotype's fitness. So sometimes they may look like it's not changing or the performance not changing, but what's actually happening is that it's trying its best to increase the average population, the overall population's fitness. It's trying to get everyone better or everyone up one more level. So on easier maps, it's recognizable that once cars have mastered steering, they aim to increase their speed, which was on the oval map that I had. This is another way they can earn more fitness in less time. And this results in the cars attempting to race each other, which is something really cool to see how the AI start to try to do better than each other. And over time, multiple species begin to form, and the difference in their performance is visible. So sometimes there's a slow species and there's a fast species, and eventually the slow species dies off. That's the extinction number goes up, which means the number of species that went extinct, and the alpha species will survive. And so that's all for my video. Thank you for watching through all this. And my source code is also available on my GitHub account, which I have linked in the presentation for this video. Thank you.